For Chapter 10, there's definitely a bunch of memorization. Starting out here, we have the difference between populations and samples. A population is everything or every person we want to understand, where a sample is everything that we have sampled. It's everything we have information on that we've gathered data on. An important term that is not on here is the sample frame. The sample frame is everything we have access to. Now, going down in order of magnitude, you will always see that the population has to be equal to or bigger than the sample frame, which has to be equal to or bigger than the sample. This is because you can only sample from your sample frame, and your sample frame is everything you have access to in the population that you want to understand. So technically, you could have a sample frame that is the whole population. You could have the list of all students at the University of Tennessee, and you want to understand all students at the University of Tennessee. And if somehow you were able to sample all students at the University of Tennessee, it would no longer be a sample, it would be a census. That is CENSUS, like the US does every 10 years. We have a census, and we get information from everyone. So important terms right there: population, samples, and sample frames. Next, we have the difference between parameters and statistics. And this part right here is very important because we need to remember SSPP, which stands for Sample Statistics Population Parameters. Statistics are from samples. Parameters are for populations. And lucky for us, they are linked right here. Do not confuse the two. Statistics are for samples and parameters are for populations. And also importantly, we do have some of the notation here. And let's take a look at this. Okay, this is from Chapter 10 notes. And you'll notice we have some important notation. I like to say the Greek population. And these are because they are the parameters. And most of these are Greek letters, except for P here at the end. And we have small sample statistics, because they're small letters. Small sample statistics, the Greek population parameters. And you'll notice that we have some that are pretty easy to remember, like standard deviation is S and sigma. I like those a lot, and you'll see those throughout the rest of this class. So it's probably a good point right now to make sure you've written down sample standard deviation is S and population standard deviation is sigma. Another good one on this page right now, y bar is the sample mean for variable y, and mu is the population mean. Also, we have on this page p hat, which is the sample proportion, and p, which is the population proportion. Something else that's not on this page, which will come into use later, is q. P and q are complements of each other. That means 1 minus p is q. So if p is 0.2, q is 0.8. And also p hat and q hat are complements of each other. It's just for the sample then. So if the sample proportion is 0.2, the complement of the sample proportion is 0.8. And that'll come into play later on. But this is some great notation right here: sample statistics versus population parameters. One of the important slides that we have goes over representative samples. Now, to do a representative sample, we do not want there to be any bias. With that in mind, it also doesn't matter how large of a sample we take. It matters if that sample is representative. So we could take, as the slide says, 10,000 people from Knox County or 1,000 people from Knox County. As long as we did it representatively, then we would get as good of results as if we did it and tried to understand the United States with 1,000 individuals. It doesn't matter how much you sample, it matters how representative your sample is. That's very, very key. We always want representative samples. And you'll notice down here when we get down to the random sampling methods, those are meant to be representative. Next, we have the sampling frame, and we've covered that because it would be right in between the population and the samples. One other thing that's not on here right now is the parameter of interest. The parameter of interest is whatever we're trying to understand. And you'll see parameters on there. Parameter of interest is just, we want to understand the true proportion. So we'd go out and find a sample proportion, try to understand that, and see if it gives us insight into the true proportion. It's like, what percent of UT smokes? Let's figure out the sample proportion that smokes and see if we have evidence that less than 50% of UT smokes. Maybe we want to figure out the average height of a UT student. Now we want to understand the true mean height of UT students. So you can see whatever it is, if it's quantitative or categorical, the parameter of interest is going to depend on that. We would have where we want to understand the true mean, which would be a parameter right there for the population, and we'd collect data the sample mean to understand that. The parameter of interest is just whatever parameter you want to understand, and you would collect a sample to understand that. Next, we have our bad sampling methods. And I love thinking of ways to sample poorly, because if you were to ask people, hey, do you like fantasy football? Want to take my fantasy football survey? You'll get free stuff for doing it, free fantasy football stuff. Well, the people who would be most inclined to do that are going to be the ones who like fantasy football. And you're not getting a representative view if, you want to understand, do UT students like fantasy football? And if you just hold up signs like free fantasy football stuff for people who take the survey, it's a really long sign. But, like fantasy football survey, win free stuff, people are like, ooh, I like fantasy football. And ESPN's hired you to figure out like what percent of UT students play fantasy football. You're going to get all the students who play fantasy football, and you're not going to be able to understand. You'd be best to hang outside and try to get random students to talk to you. And we'll get down to better ways of doing that later on. But definitely getting people to volunteer to take your survey adds in voluntary bias. Lots of problems there. Convenience sampling is the chosen sampling method, the method of choice for a lot of people in a lot of classes when they're told, your survey is due in 5 hours. And they're like, oh no. So they walk outside and they immediately talk to the first 20 people they see. A lot of ways, convenience just means it was done in a convenient way, which is not random. If you speak to the first 50, the first 100, if you throw it up online, a lot of times that's not really random. There's good ways to do online surveys and there's bad ways. But if you just send it out to your friends on Facebook, that's more of a convenience sample because you're not really randomly sampling UT students. So convenience is when you do it in such an easy or quick way that it just wrecks through any sort of ability we have to put the results onto the whole population. Maybe you want to do a survey on, what presidential candidate are UT students voting for? And so you put it up on Facebook. And, some of us have a lot of friends over different political ideologies, but they say, usually you gravitate towards people who have similar ideologies. So people who support candidate X might have friends, are more likely to have friends who support candidate X. So all of a sudden they're like, oh, UT really supports this candidate. I went and put it on Facebook and everyone responded. I got 1,000 responses. And wow, UT is in overwhelming support of candidate X. But no, you did it in such a convenient way that no, the results do not generalize. Next, we get to the really random sample. Next, we get to the ways to truly random sample. And let's take a look right here. The simple random samples. For this right here, we need to make sure we enumerate the whole population and everything in the population has an equal and likely chance to be selected. So that's two parts right there. Part one, enumerate the whole population. Part two, everything has an equal and likely chance to be selected. So you could get the, numbers, you can get the student ID numbers from the university registrar if they'll give them to you, and then just start randomly generating UT student IDs. Or you could put them on a list 1 to 35,000 and just generate a number 1 through 35,000. The random number generator is not going to generate the first random number or the last. No need to mix them up because the random number generator will do its work. So everything is enumerated, and when we pick a number, we pick that person. If you think about that, if you chose 1,000 UT students at random and you asked them who they were voting for by that method, you'd get a pretty good view into it, because why would you be picking too much or too little of a certain supporter of a candidate? That would work great. Next, we're going to skip on down to systematic samples. I like doing that one next. Systematic samples is when you select every kth item, and you must start at a randomly selected point. And the reason I mention that is because there's two parts to this. You need to pick a random starting point, and that's not multistage. You pick a random starting point, and then you select every kth item. So maybe we are going to get that list of UT students, and we're going to use the random number generator to generate a random number. And it's going to say start at student 15,842. And then from there, we're going to go down the list and we're going to take every 20th student. You can do this other ways. You could use a random number generator to figure out what time you're going to go to campus. And you could say, okay, I'm going to do sampling on 5 different days. And on those 5 days, I will hang outside the library at a time between 8 a.m. and 4 p.m. And I will sample 50 students on those 5 days. And then I will do it by a systematic sample. Every 10th student who walks by me, I will ask them if they want to take my survey. So you count as 10 students walk by you, and then you ask them if they want to take your survey. So I'm going to have to use the random number generator to find out what random time I'm going to have to go to the library on those days, and then I'm going to use a systematic sampling method, which includes that random time, to then sample every 10th student. Student walks by, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, sample that student. So once again, the two parts to a systematic sample, and this is not multistage, this is just systematic. 1, pick a random starting point, and 2, sample every kth element from then on. And kth could be 5th, 10th, 20th, 3rd, 4th, whatever you want. Next, we get to the doomed, stratified, and cluster. So with this right here, I want you to think about what strata means. Strata in Latin means layers. So with that in mind, layers separate things. You could think about, a cake you have the icing layer and then you have the cake part. They're separate. And think about that. If you were to sample that cake, you would say it's, like 5% icing and 95% cake. So you wouldn't want to just carve off the side of the cake with all the icing and be like, this is a true sample of this cake. You'd want to get a slice that looks representative of the cake. So strata is sampling in accordance to the percentages that exist in the population. It's acknowledging differences, that the icing and the cake part of the cake are different. So let's think about some examples here with students. If we acknowledge differences in students, we might say we have athletes and we have non-athletes. What if we were talking about building a new stadium or building a new dorm for athletes, which we're doing right now, and we were to ask students, do you think we should do this? We wouldn't want to sample too many athletes or too few athletes. If UT is 5% athletes, we'd want 5% of athletes in our sample. So this right here is where we sample and make our sample look like the population because we want it to be representative. Strata is acknowledging differences. There's a difference between how athletes and non-athletes might feel on this issue. So with that in mind, we should sample in accordance to those differences. It's also important to note when we have this strata, we have to sample randomly inside the strata. So this means we'd randomly sample 5% athletes and we'd randomly sample 95% non-athletes. That's how we would find those students. Next, we get to cluster. And cluster is going to sound similar, but it's very, very, very different. A very short and easy definition of cluster would be to take a whole bunch at once. But that doesn't quite cut it. Let's make a better definition. When we do cluster sampling, we have groups that have been put together at random, such as like bags of M&Ms. They don't put all the bad M&Ms in one bag or all the good ones in other bags. It's kind of just random. Sometimes, bad M&Ms just kind of get into a bag. So if we were to go to the M&M factory and sample bags of M&Ms, those bags would be clusters. When we get the bag, we sample everything inside of the bag. We take the bag, we open it up, and we figure out how many bad M&Ms are in the bag. The way we find the bag is to find it randomly. The clusters are selected at random. So let's break down cluster again. What you have is the population has been put into clusters that it has been assigned to randomly. And this is like our bags of M&Ms. We didn't put them in certain bags for certain reasons. We're not saying, peanut butter versus chocolate. That'd be stratifying them because we're acknowledging a difference. We're just looking at chocolate M&Ms and looking at the bags. So we find a random cluster, and then we sample everything inside that cluster. And of course, we can sample multiple clusters, and we'd find them all randomly. We'd use a random number generator, find that bag of M&Ms at random, and then we would sample everything inside of it. Stratified, once again, is that we divide the population into different strata that we think might have some sort of difference. We can do this at the M&M factory too. We say, well, maybe we produce 80% regular and 20% peanut, and we want to see if there's problems at our factory. So in our sample, we should have 80% regular and 20% peanut. And now when we go out and sample, if we sample 200, we would sample 160 M&Ms that are regular and 40 that are peanut, because 160 out of 200 is 80% and 40 out of 200 is 20%. If you notice, our sample goes in accordance with the percentages in the population. And a really great thing right here is we can then go to a multistage. Lots of ways to do multistage. We could stratify and do 80% of our factories regular and 20% is peanut, and we could then take 80% bags that are regular and 20% bags that are peanut. And so we could do stratified to start and then take the samples via clustering. We could stratify the population and we could say, okay, 80% regular, 20% peanuts. And then we could say on the line that day, we need people to pick a random starting point and sample every 20th M&M. And so then they're going to sample every 20th M&M, and then we've added an element of systematic. Take it a step further, and we can put it to clustering, and we could say on the line, on the regular and on the peanut line, we need people to sample every 20th bag that day. So now we make sure our sample is 80% regular, 20% peanut. That's the stratified. We have them taking every 10th, I think I said, every 10th, and that's systematic right there. And when I say bag, that is cluster. So there's a lot going on right there. A lot of these include an element of simple random sample. So don't get confused with multistage being, well, in the clusters, you have to find the clusters randomly. No, that's just an element of cluster sampling. With stratified, you have to sample randomly within the strata. No, that's just an element of stratified. So a few ways to combine them together right there. Next, we go to bias. And this is a pretty fun one right here because you get to think of some crazy things that go on when you do surveys. When it comes to bias, we have non-response bias. And this is right here when you do not get the response. And oftentimes it could be something about the survey itself. They could quit the survey, but the person refused to respond. And a lot of times this is because it's not at random. The person hangs up on the phone. Maybe certain households don't want to speak to you about certain issues, or certain groups might be less likely to take certain types of surveys, and this creates bias. We don't like this because then we're not actually getting the right representation in our sample. Next, we have undercoverage. And this is often the fault of the researcher themselves via the sampling method that they created. Because when you have undercoverage bias, you leave out an important voice in your survey. So maybe the athletes are all on a trip away and someone does a survey about building a new stadium and they say, oh, all of UT doesn't want a new stadium built, or some sort of issue related to athletes, and all the athletes are at some big conference and no athletes make it into the survey. And that's because none of them were in the sample frame. We still want to understand them. They're in the population. And they weren't in the sample frame because we had no ability to sample them. Sample frame is everything you have the ability to sample. So if you don't have the ability to sample them, they can't make it into your sample, and thus your sample could never be representative. So in that instance, we have some undercoverage bias. And last but not least, we have response bias, which is when the bias is in the response. And sometimes the question itself can give bias. If you say, I think one of your homework questions is like, given that 18-year-olds can get married, go to war, and drive a car, and buy cigarettes, do you think it's fair that they can't drink? And someone else could write the question, given that raising the drinking age has stopped a lot of drunk driving and probably saved tons of lives, do you think we should keep the drinking age where it's at? And I'm not taking a stance on this issue at all, but the wording of a question can induce bias. You're not trying to do a survey where you see if you can convince people to believe a certain way. You're doing a survey to see what the general public's view on the issue is. Because when it goes to a vote, the law is simply going to be change the drinking age to 18. And there's going to be no preface before it trying to push people to either side of the issue. So you don't want to induce bias, and a lot of different things can make people give a response that's not their own. So anytime the response is not their own response, somehow they're misleading, maybe they're lying, maybe the question is pushing them towards something they truly wouldn't answer, that is when the bias is in the response and it is not representative of the population. Like if we were to go out and do this on a mass scale, we would not get a representative view. And that was our goal all along, to understand the population, to understand some parameter in it, via representative sampling. Good luck. Email me if you have questions.